Right. Good morning, good afternoon, or good night, depending on where you are. Welcome to the industry session at Embedded Systems Week. We have an interesting program with 4 talks over different branches of industries, also very different topics, covering the whole range of Embedded Systems Week. And I would like to start by introducing our first speaker, Binyi. Binyi is currently a PhD student at Infineon and TU Dresden in Germany. And his main research interests are the optimization of neural network algorithms and the design of neural network hardware accelerators. As you might have also already guessed by the title of his talk, Towards Agile Design of Neural Processing Unit. Binyi, stage is yours. Please share your screen.
Yeah, thank you. Yeah, can you hear me and see my screen?
Yes, very good. Please go to presentation mode.
Yeah, it's
exactly perfect.
Fine. Yeah, thank you. I'm Binyi, and I'm from Infineon and TU Dresden. Today, our topic is towards agile design of the neural processing unit. I will first talk about the motivation and then the approach. Afterwards, the experiments and the conclusion sections and the talk. Let me start with the motivation. Our project is for designing an edge neural processing unit for inference. Designing of the NPU actually is inseparable from deep learning ecosystem because there are a lot of state-of-the-art neural algorithms relied on them, and it's also inseparable from corresponding underlying software. For example, the mapping strategy, how to configure the NPU to accelerate a specific operation. Designing of NPU is involved a hardware design, software design, model. Then we need to deploy the model, and then finally we need to evaluate the performance. So it's involved both the hardware and the software design, so that we required agile approach to increase the synergy between the hardware and the software development, speeding up the prototyping and the NPU the evaluation. It's especially very important to help us to find out the bottleneck of the NPU, and so that we can propose some solution to address this bottleneck. And this is very important, especially at the very early stage. The next, I will talk about our approach. First, we parameterize the NPU design with Chiao. Chiao is based on Scala, a very high-level language, so that we can very easy to modify, the extend, and maintain the design. And this is the general architecture of our NPU. The MVM is for storing the model parameter, and the SRAM is for the activation. And they will be cached into the buffer and then fetched in, and then the data will prepared by the wait processing unit and the activation process the unit, and fed into the computation unit. And this design has 5 configuration option: the size of buffer, number of bank, number of MAC, number of bias, which is for adding, and the number of the scaling, which is for recompensation. Yes, we call this instant configurations. If we change them, they will generate a specific NPU. And the second step is our second proposed stuff is the customized Chiao backend, because the Chiao size is written in Scala, but on the software side, we want to use the deep learning ecosystem like the TensorFlow or PyTorch, and they are in Python, so that we need a component to connect the Scala and Python. And so that the Chiao backend, our Chiao backend is for this. They will deliver the new hardware design to the software development on Python end. It's basically it will compile the Chiao source code and generate a clock accurate simulator, and this will contain C++ and the Python API. It will prepare all the interface for the Python end. So fast, and it is end-to-end solution, just one click and it will do all the stuff for us. The third component is the Python software stack. As I mentioned before, it integrates with TensorFlow, so that we are staying closer to the ecosystem, and will help us to avoid some user level bug. And it also facilitates for us to develop the mapping strategy, and we can also do a very quick performance evaluation. And with the help of the Chiao, we can expose the internal state of the MPU, so that the software can get a very detailed performance profiling, and help us to understand the bottleneck of the MPU and the feedback to the hardware side for optimization. This approach, as you can see, is a pure software approach, and only involve Scala and Python, and they are all very high-level language, and which help us to apply the Agile software development method, the continuous integration and continuous delivery and deployment. It will make the design flow fully automated, and save a lot of time, shorten the development cycle. Next, I will talk about the experiments. The first is I would to show how much time does it take for the whole process. If we modify the design, it will do the elaboration, and it always takes minutes, and then step into the unit test. This is a user-defined unit test, and all this will be done in the Chiao backend. And once it passes the test, it will deliver it to the software stack. And on here, there is a simulation-based verification, and the list will take minutes or up to a few hours, depends on how many tests we want to do. And finally, it's deployed. Once it passes the validation, it will deploy it for further development. The whole process actually in general takes a few minutes, and much faster than conventional prototyping approach, for example, the FPGA. The next, I will show how it helped us to discover the hardware bottleneck. With help of Chiao, we can expose the internal state. For example, the SRAM's operation, NVM operations, buffer, input buffer operation, and wait buffer operation. And the first row is the it shows for 16 meg and with 18 kilobyte weight buffer, the meg utilization is very high, almost 100%. But if we increase the number of meg to be 32, but keeping the same weight buffer size, the even with the best runtime configurations, the Mac utilization is super low, lower than 20%. And if we take a look the internal state, we will find at the MVM the bottleneck the overall system performance is because the weight buffer is too small to hold the 32 filters. And our solution is we introduce the Mac array reshaping, and in the row 3 we reshaped it to be 2x16 and still having the same weight buffer size, and the Mac utilization will goes up to very high again, over 96%. And in this case, each time we only need 16 filter, and so that 18 kilobytes weight is sufficient. And if we even reshape the Mac array to be 4x8, we can even reduce the weight buffer, but having a very high Mac array utilization. And this is a case so us showing how to discover the bottleneck and how to address it. The next experiment is the Python software stack can help us very good to understand the NPU. Except the Mac array I introduced before, there is a memory. There is a buffer allocation. The buffer is composed of the multiplied bank memory, and in this case, this shows how many bank of memory we allocate to the to input, and the remaining will be allocated to the weight. The output is 0, and we can see here once we change both of them and how the Mac array utilization changes. If we keep the Mac array shape the constant, and we reducing the input buffer size, which means the more buffer will be allocated to the weight, and the Mac utilization increased slightly. And if we keep the banks allocation scheme constant, but we increase the NS, and we can see the Mac utilization increased dramatically, and up to almost to over 90 or almost 100%, I would say. And this so give us some intuitive feeling how the runtime configuration impact the NPU performance. And the last experiment is in our method we use the software stack to collect a massive data set, so that with this data set we use the AI-driven method to learn because we have a very rich combination of instant configuration and runtime configuration, and we can use this data set to learn how to get the optimum mapping strategy based on the operation and the design performance we want. The design performance here means the shortest latencies or low or fewest memory operation, and we can even input the operations and the mapping scheme, and we can estimate the performance of the NPU. Yes, next, the last section is conclusions. Our proposed method enabled software and hardware software co-design in a pure software approach at the very early stage, and shortened the development cycle. And this method is not unique to NPU, but can also be extended to other projects. And the next step that we will conduct design-based exploration to find optimum NPU design for a specific application scenario according to the area and the NPU performance. Yeah, thank you for your attention.
Okay, thank you very much, Binyi, for this very interesting talk. Is there any question in the audience? not, I would like to postpone questions to the poster. All the presenters will be present in the poster session directly following this session. And I would like to come to the next presenter. Chiao, you may already present and share your screen. So Chiao Hsieh is a PhD candidate at the Department of Computer Science in the University of Illinois at Urbana-Champaign. And he is doing research there with Professor Sayan Mitra in the Reliable Autonomy Group. His research direction is to obtain the provable safety assurance on cyber-physical systems, in addition to field testing and software simulation. So, Chiao, the stage is yours for the talk, Challenges in Rebooting Autonomy with Deep Learned Perception.
Yes, thank you. Thank you for the introduction. Hello, everyone. My name is Chiao. I'm sorry if I sound a little bit tired. It's 3 a.m. here. Today, I'm going to present our industry track on the challenges of ensuring reliability with autonomous system with deep learned perceptions. This paper is a joint work with our collaborators in the Boeing company and also my colleagues in University of Illinois at Urbana-Champaign. So this paper is about teaching these challenges in ensuring reliability. So we know that nowadays deep learning models are becoming very effective in solving computer vision related tasks, and such as object detection, lane tracking, lane detection, or semantic segmentation. And these models are data-driven and are often updated through the life cycle of a product. And we consider that there's a need to develop new methods for the reliability assessment and operational process for these autonomous systems integrating these deep learned perception components. So in this talk, I'll quickly go through two examples, simple example systems using AirSync, and then we will talk about the challenges even in these very simple example systems. So our first system is from the AirSync drone racing competition in NeurIPS 2019. So in this racing competition, there is a perception only track. In this track, the competitors are using the same tracking controller and the drone dynamics to complete racing track. But the perception task in this competition is that it needs to use the front camera image to detect the gates that defines the racing track. And then it has to use this image to guide the drone to pass through each gate successfully. So on the right is the videos that's showing how you use some vision components to detect the gate and then pass through it successfully. And a quick side note that all the top 3 winners in this tracks use a certain kind of image neural network in order to identify and pass through the gates. And our second example system is a vision-based swarm formation system. This is this is motivated by the fact that some of the environment, there is no GPS, so they use this camera image. So in particular, in this system, each drone will use its downward facing camera images and then compare it with its neighbor, the image or image features from its neighbors and matching the features in order to obtain this relative position information. And then with this relative position information, there are classical formation control algorithm in textbook that can help you achieve the formation control. Yeah. So even with this 2 simple system with very simple perception components, we identified 3 challenges. The first challenge is about defining what is the specification for this perception components. And in our two example systems, this particular perception task is actually a kind of what we classify as a state estimation task. It is estimating the positions of the drones. And for this kind of perception task, it is important to know first what is the accuracy, but also very, very importantly for this vision-based perception is that what is the expected operation domains for these perception components that will work well. And we consider this perception components as a high level of sensors, if you may, then it should come up with something that is close to, for example, a GPS sensor that what is the accuracy for your position output, and how do you formally, the more challenging part is how do you formally define the particular operational domains for each of the different environments. Our second challenge we identify is that given we have the data sheets from for the perception components, how do we use this information for the system safety assurance? Basically, how do you test and verify the whole system with this kind of perception components? So one of the approach we think about is that if we can use, if we consider the perfect state estimation for example, positioning system, then our example system now becomes a standard cyber physical system, and there are many testing and cyber verification techniques. But the problem now is that in this new type of way of specifying the data sheet, including this operational domain for the perception components, how do we really propagate these assumptions on the perception with the operational domain to the system level analysis? Finally, we identify this, the third challenge is about the runtime assurance for the system. So basically, we cannot expect the system to always run in the operational domain specified in our data sheet. Then in this case, it is important to know when it is out of the, when is your perception components operating outside of your operational domain, and how do you deal with these out of distribution perception inputs? So in our formation control systems, we observe that one of the perception tasks, one of the intermediate stage in this perception pipeline is this feature matching between the camera images from neighboring drones. And we observe that for example, the weather, the fog levels affects this perception, this particular stage very significantly. For example, the fog level increased to 0.05, there's barely any matching features. So how do you monitor the system performance when it is under different operation domain? And then first you have to detect it, and then how do you react to it? So in summary, I introduced the three challenges in our described in our paper, namely, how do you come up with a specification that is specified as a data sheet for this high-level sensors? And then second is, given this data sheet, how do you conduct system-level verification and testing, given this data sheet is only for your perception components? And finally, I described the challenges in runtime assurance. How do you detect and react to when you are operating in outside of the operational domain? And I want to mention that all these air scene simulation code is available online. You can find it in our website. And if you have any, if you want to know more about the project, you can contact me through my email. Thank you.
Thanks a lot, Chiao, for this very interesting talk and outlining those challenges since you're working in that direction, I'm sure you already have ideas about approaches. Would you share to give us some, some insight in that?
Yes. I forgot to add more about myself, and we actually have MSOF paper in the safety and security session this going to be for my time, it will be in 9 a.m. and it is about very relevant direction. We provide the reliability for lane tracking system for autonomous vehicles. It's different from this drone racing and drone formation scenarios. Our idea is exactly following this direction, that how do we formalize this data sheets, and we follow the same idea I just mentioned, that can we specify something like really close to what you will specify, a GPS sensor. The idea is that the GPS sensor also takes a unknown ground truth position of yourself, but then it actually provides an estimated mean value or estimated position of you with some bound of error, and that kind of things can serve as a data sheets for us. Still, there's the challenging part for how do you really define the like the expected operational domains for a given, let's say, although you have the accuracy, you have to define this accuracy against the perception components you have. It's still a huge, like a high dimensional vectors, how you can vary the environment, as you can see in this particular examples for gate detection. And yeah, so that's one. We have that for MSoft, and then we also have submitted a paper about this drone formation to ITRA, and I'll be happy to talk about that offline with anyone who is interested. Yeah.
Okay, thanks a lot. Are there any questions from the audience? So if not, then I would like to thank you again, Chiao, and please visit his poster and engage in discussions with him. And I would like to come to the next speaker. That will be Alberto Laurauri. Sorry. He is a PhD student in the program of Applied Mathematics at Barcelona Tech. And he also works as a research assistant in the systematic construction of correct systems group at Technische University of Graz. And his work there focuses on extending formal techniques developed for finite state machines to multi-component systems and on applying machine learning techniques in the verification of continuous systems. And he'll talk today about surrogate models for testing analog designs under a limited budget. Alberto, so stage is yours. Please share your screen.
Yes, sorry, I am here. I was not very sure how to do this. Do you see my screen right now?
Yes, perfect.
Can you see my pointer as well?
Yes, also this is working.
Perfect. So thanks a lot for the introduction. My name is Alberto Laurauri, and I will be presenting this industry paper titled Surrogate Model for Testing Analog Designs Under Limited Budget. This is joint work with partners at TU Graz, AIT, and Infineon. So our case study consists on an analog voltage regulator provided by Infineon, which is an analog device whose objective is to provide a stable voltage under a variety of external conditions. These external conditions are given by a temperature and a variety of external voltages. And this device attempts to always keep its output voltage within the specification interval shown on the screen. So our goal for this work is to verify this device. We do not perform verification at physical level, so we do not work with physical circuits, but instead we work with very accurate simulators, which are able to emulate the behavior of physical circuits with high accuracy, but they take a long time to do that. For this reason, practical verification approaches should attempt to use as few simulations as possible. In our case, the device is not very complex as far as integrated circuits go, but even then, we can see that simulations take a few minutes. So sometimes 2, sometimes up to 4. So approaches that use, let's say, tens of thousands of simulations should not be considered. Something that you encounter when you look at these kind of problems is that existing techniques suffer from the so-called curse of dimensionality, meaning that they scale very badly with the number of input dimensions. So in our case, to circumvent this problem, we use domain knowledge to reduce the number of input dimensions. In the table shown on the screen, one can see the input parameters of the voltage regulator together with their typical minimum and maximum values, and the comments provided by Infineon's engineers. Using these comments, we can reduce the original number of input parameters, 6, to half of it if we make use of their instructions. So during the verification of the voltage regulator, we have 2 goals. We focus on the main one here. The first goal is to produce cheap and accurate surrogate models of the device from as few samples as possible. These surrogate models should imitate the behavior of the voltage regulator, and when we say cheap, we mean they should be cheap to evaluate. So they should not take minutes to produce a result. We are talking about seconds at most. And this is important to us because these cheap models can be used in the second objective, which will be to find critical test scenarios. Critical test scenarios will be input values that drive the voltage regulator out of the specification, or in the case the voltage regulator is correct, hopefully. What we try to find are values, input values that drive the regulator to extreme outputs. For these tasks, we use 2 kinds of machine learning models, which are Gaussian processes and neural networks. And what we do during this work is we compare these multiple techniques and try to establish which one works best for this particular scenario. During this presentation, we will focus mostly on the first part, which is obtaining cheap surrogate models. But in the paper, one can find more about the second part, which will be finding critical tests. Now, moving on to the statistical models, without going much into the math definitions, Gaussian processes are statistical models that can be used for regression of unknown functions. And these statistical models have a very attractive feature, which is that they hedge their predictions, meaning that they do not only give predicted values for the objective functions, but they also give a confidence range for these predictions. So we can see a picture on the screen. Here, there's an objective function, which will be the dashed line. There are a few samples that we have taken of it, which will be the black dots, and fitted along the samples, there's a Gaussian process whose prediction is represented by the solid black line, and it also gives us a confidence interval for this prediction around it, which would be the blue area. So this confidence interval decreases close to the prediction and increases when we are far away from them, representing a higher amount of uncertainty. In order to obtain Gaussian process models of the regulator, we proceed in 2 steps. The first one, we just do an initial fit of the Gaussian process using a small number of initial random simulations. Here we do all the hyperparameter training, scaling, and all those things. And afterwards, we proceed onto a so-called adaptive sampling phase. And in this phase, we are choosing each new input location for each sample successively, trying to maximize some underlying objective. We follow 2 different strategies and compare them. The first one is maximum entropy sampling, and the second one is Bayesian optimization. So in maximum entropy sampling, what we do is we want to obtain a globally accurate model. And for this, we pick each new simulation at the location that maximizes the uncertainty of the current model. So shown on the screen, we have a current Gaussian process, and we pick the point where the blue area will be the widest for the new sample. And we proceed until the budget of simulations is depleted. The second approach, which will be Bayesian optimization, is a well-known black box optimization method that works. That works kind of similarly to maximum entropy sampling, but here we do not pick samples that maximize the uncertainty, but instead pick samples that are likely to produce extreme values of the objective function. These points then should be points where the prediction of our model is extreme, but also points where the uncertainty is somewhat high. So this way we can balance the exploration and exploitation objectives. And then for neural network surrogate models, we follow a very simple approach. We just train neural network models using random samples taken from a lattice of input values. In the following graph, we can see some experimental results. Here, what this graph plots is how the accuracy of the different methods evolve with the number of samples. The accuracy is measured in terms of a root mean square error measured on a test set. And each experiment is repeated a number of times, so that what we see on the screen is the solid lines will be the mean errors of the experiments, and the solid areas around them will be the 95 confidence interval. If one wants to see more details on the setup and the methods, like the neural network architecture, the architecture of the Gaussian processes, and so on, one can consult our paper or ask questions later. And the results, what they show is perhaps unsurprisingly that the maximum entropy sampling performs the best, as it's able to ask for samples at adaptatively chosen locations where it gains the most information about the model. And not only it manages to obtain the best or the most accurate models the fastest, is also very consistent in doing so, as we can see in the small confidence interval around the mean values of the model. However, if you remember, obtaining a globally accurate surrogate model of the circuit was not our only objective. Our second objective, which we don't have time to go in depth, was to find critical tests. And the idea for this is that to find critical tests, we can run optimization procedures on these surrogate models, which are now cheap to evaluate. For this second task, however, Bayesian optimization was the better performing. And this is explained because in Bayesian optimization, the models resulting from Bayesian optimization are not necessarily globally accurate, but they are accurate around extreme areas for the voltage regulator, which enable us to find extreme critical test scenarios. Finally, these methods are all well known, but if one wants to apply similar techniques for more complex systems, it's necessary to think about dimensionality reduction techniques, among other challenges. There are some papers in this direction for testing of cyber-physical systems using Bayesian optimization, but it is fair to say that this is an area where there's little work and more work is needed. And yeah, this is all for my part. Thank you for your attention, and I will be happy to answer questions.
Thanks a lot, Alberto. Are there questions in the audience? Otherwise, I would like to just hear when you said on your last screen that Bayesian optimization is most critical or is most suited for finding the critical scenarios. You gave a qualitative explanation. Have you also verified that quantitatively? And how did you do that?
Yes. So there's another graph here, which is harder to read. So what we did afterwards, of the second part of our work, was to use the surrogate models to find these tests. And what we did was to take these surrogate models and run an optimization procedure on them. And what we did was take these optimum values where the voltage regulator should give, for example, a very high output. We find these values on the surrogate models, and then we go back to the real thing, to the simulator, to see whether these are good tests or not. So, and in this regard, on the screen, there are many things that I have not talked about, but for example, here you look at the maximum search, and there are many lines, and we focus on the first three ones. The other one is the baseline. And Bayesian optimization here, you see that it's increasing rapidly, and it's very consistent. It's worth noting that the values that Bayesian optimization gives are real values, are real simulation values. And the other methods also perform well, but they are sort of inconsistent. And another disadvantage that they have is that they tend to over-approximate in their predictions. So the values that the other models are showing are not real values, are values that when we go back to the simulator, are usually way lower than the Bayesian optimization values. So this is a little bit hand-wavy, but more details can be found in the paper.
Okay, thanks a lot. Any more questions from the audience? Otherwise, also time's up. And let's go to the next and last but not least speaker. So that's Kai-Björn Gemlau. He is working at the Institute of Computer and Network Engineering, IDA, at the Technical University of Braunschweig, pursuing his PhD there, and working together with Professor Rolf Ernst, and is working in the German Unica Agile project. And his research interests include real-time communication for distributed cyber-physical systems, including TSN networks and network stacks. And he's reporting on system-level LED in AutoSAR, a joint work together with Mercedes-Benz. So Kai,
yeah.
Stage is yours.
Thanks, Dirk, for the kind introduction. So yeah, this talk is about system-level logical execution time in AutoSAR. So let me start with a motivation. If we take a look at a modern vehicle, we see it as a heterogeneous and shared platform. So we have different types of controller, different types of hardware here, but also in the software, we see, for example, AutoSAR Classic, which is more like a real-time operating system, and AutoSAR Adaptive, which is more like a Linux system. So quite complex platform. And now we have the challenge to integrate different distributed applications which have end-to-end timing requirements. For example, in automated driving, we see the sensor fusion, perception control pipeline, so everything from sensors to actuators. And in the design, of course, we have to keep the end-to-end deadlines because this is a safety critical system, but also, which is quite important, we have to preserve the data flow, the consistency, because the data flow is important for the correct functionality. So for example, if you combine different sensor samples, you want to know that you combine the correct sensor samples to get your perception. But also we have to keep an eye on an efficient design and maintenance process here. So we have to include applications that have more runtime dynamics, such as image processing and so on. And we want to enable updates within our vehicles as easy as possible. And this also has to do with a interaction between the OEMs and the suppliers. So how can we talk about those timing aspects between the different parties? So if we take a look at a task which executes on a real-time platform, we normally have a physical execution which has a response time varying between the best and the worst case. And the idea of the logical execution time is to put a logical wrapper around this. So we have a deterministic execution time abstraction where we say we have a constant time interval between a read and a write instant, which we call the LET. And at the read instant here, the data is read in 0 time, and the output is not written as soon as we finish execution, but we define a specific point in time where we publish our output to the subscribers. And this combines in an uncertain computation timing with a deterministic communication timing, which helps us in some parts. So LET systems are time predictable, of course, and then data flow deterministic. So we know which job reads from which preceding jobs. And we also have a kind of platform independence here, because every implementation that fulfills the LET specification that has a response time smaller than the LET will behave the same, which is quite important. And it's also composable. So let's say the timing is made of building blocks. Those LET intervals are somehow building blocks for timing. And this is very useful in the context, for example, for multi-core communication. We can implement log-free communications. Our colleagues from Mercedes have shown this in various examples. But it also, as I said, it enables easier software updates, platform modifications, and those building blocks are quite helpful if we talk about the interaction between the suppliers and the OEM. Why not simply extending this to the system level? Well, the worst case response time for a task is has to be smaller than the logical execution time, and this has to be smaller than the period, which is a quite strict restriction here. And we have to provide the output data to any subscriber in 0 time. And if we talk about the distributed systems, this would also require the perfect clock synchronization. And if we go to the system level, we see new requirements. Our latencies may be larger, far larger than the sampling periods there. And we will have distributed clocks, which we can only synchronize up to a bounded jitter. And at the end, we want to extend this idea not only to this task level, but also on a higher level in design stages earlier. So therefore, there's an extension called system level LET, which was first meant to abstract communication. So for example, I have a system here with 3 ECUs, and they are connected with a bus and an Ethernet network. Can be summarized, we have to identify LET zones, so zones where we have a local time base, and we can synchronize those LET zones sufficiently, not perfect, but sufficiently. And then we have to model the communication between them in a specialized LET task, and we can do this here. So our LET zones are a subgraph of the platform with a local clock. We can synchronize the clocks, for example, by means of precision time protocol, which is implemented nearly everywhere. And then the important aspect is we have to model the communication here with those interconnect tasks, and we have an extension called the permitted pipelining, which allows us to have a logical execution time larger than the period. And this is always possible under the pipelining assumption, for example, for communication. But also, if we take a look at some image processing, so the perception pipeline, it's also in the word there. Some image processing tasks or so, they have larger latencies than their sampling periods, but they work in a pipeline fashion, and there it's also applicable. And this interconnect task in the first step, it abstracts, let's say, the communication stack at the sender side, the network in between, and the communication stack at the receiver side. So we have an abstraction for this whole communication path between 2 local LET tasks. And that's it. That's a minimum LET extension, which is going in the new AutoSAR release this year. And it has some other benefits in the design process. As I said, it's already applicable on a quite early step in the design. We want to put it also on the functional level. So let's say we want to specify timing of any blocks, we call them. So a functional block or a task, why make a difference? Starting on the functional level, we can follow the constant process of defining and decomposing time budgets for communication and computation, which is again helpful for contracting between OEM and suppliers. There's also a pending AutoSAR concept for this unified timing approach. And the idea is I specify my system level LET model on the functional model, and then I can decompose it and have different variants, different integrations, for example, implementing it on 2 ECUs, some remote, some local communication, or in a single ECU or between 3 ECUs, but it does not matter. It behaves the same. We have the same data flow. And this is quite important. For example, if we want to ensure that the function 3 here combines the correct data samples produced by function 1, independent of how long the communication takes between those blocks. But there are also other possibilities here in the design process. So first of all, that we have a flexibility in the specification. Those LET zones can be described hierarchically. So we can have a specific description. For example, one ECU has a local clock. It builds one LET zone, but we can also provide some abstract hierarchical wrappers, something like the LET zone of my vehicle, which is not a specific clock, but it can be specified that this inherits the synchronization accuracy. And then I can specify my SLLET intervals for the interconnect tasks, either specifically between those ECUs here, or I can also specify it on a higher hierarchical level. If I have not yet a platform specification, I can say, okay, it's at least that good synchronized. And this is quite helpful in the design process. With further benefits I want to keep out of here, something like the composition of existing LET systems, so we can take what's already existing in the design process, what we have also specified in AutoSAR yet, we can compose it. We can also analyze the robustness. So this question, how long am I platform independent? When is or what behaves the same and when do I get problems? So how much robustness do I have in my system? And we can also incorporate something like virtualized platforms and so on. That is out of scope for this talk. So to summarize, the system level LET model only comprises a few additional model elements like the LET zones, the interconnect tasks, and the permitted pipelining. And we can cover a large set of applications there. In the first place, of course, LET for distributed systems, but also virtualization, data management, and so on, and those high performance applications where LET has not been applied yet or not been applicable yet. And this scales better to large systems, to large distributed systems, where we can use the benefits of the log-free communications we've seen in the multi-core setups now on a system level. And yeah, it's now available, will be available in the upcoming 22.11 release of AutoSAR, and some additional documentation will go in the next year's release regarding this unified timing approach. So thanks for your attention. I'd like to take questions.
Thanks, Kai. Any questions from the audience? Otherwise, let me ask you a question. So you advocated LED and also the extension as being platform independent. And you also gave this nice example with the 3 different zones or 3 different ECUs, and depending on or zones and depending on where you map them. But I mean, with every part where you introduce a communication between different zones, you add delay, right? So what is the counter example to your slide would be if I have a chain of those 3 modules, and they will be mapped only. I can only afford the delay to introduce in this chain at one point in time. So either before going to the second module or after the second module going to the third. So it's a typical thing that, you know, you have different deployment scenarios and can't afford the latency. Is there something you can do there?
Yes, this somehow depends on the. Let me go back to that slide. It somehow depends on the robustness you have in your system. So, for example, if you specify a latency which is on the lower path here, shall be the same as on the upper path. Of course, there might be a combination where we say this forward path here to ECU2 has to be then shorter and the backward longer, or the other way around. But at least it provides you the possibility to analyze this robustness. And of course, not every platform mapping will fit the robustness. But you can easily identify how much robustness do I have and where is the bottleneck in my system, and when do I need to refine my initial specification and get back to the, for example, also to the function developer and say, okay, now I have to implement a specific system here, a specific integration, which cannot fulfill the requirements from the SLLET specification. Then I have to go one step back and ask the function developer, can we refine our initial specification? Is this also okay?
All right, thanks a lot. Are there any more questions? So otherwise, I would like to thank our speakers, especially Chiao, for being available at this very interesting time for him. And I would like to invite everyone to continue discussions at the posters. You will find them in Gather Town if you just go all the way to the left along the Bund. So thanks again, everyone, and see you in the posters.